Hi everyone, I'm going to lecture resultant of non-coplanar concurrent force systems. So these are uh, 3D forces and these forces meet at a common point. So the principle is simple. We just add a third component of a force and we combine similar components. So the resultant of a non-coplanar concurrent force systems may be represented or described by force in vector form. So R equals Rxi plus Ryj plus Rzk. So all you have to do is we have to determine Rx, Ry, and Rz and write the resultant in that form. That's the vector form. So let's have this first example. Determine the resultant of the two forces shown below. So for the first force P, it is directed forward, up, and to the right. So all its components are positive. So we will compute first the xz component, which is hypotenuse times cosine of 50 degrees. So px is 400 cosine 50. This is the pxz component. Then we multiply further by the x component is opposite of 40, so we multiply further by sine of 40. So P sub x is equal to 165.3 newtons. Next, for Py, it is simply the vertical leg of this right triangle. So it is 400 sine of 50. That's P sub y. Then P sub z, which is positive. So by the way, Py is 306.4. P sub z, which is positive, is Pxz, which is 400 cosine of 50, then times, this is the adjacent side, so times the cosine of 40. So P sub z, 400 cosine 50 times the cosine of 40. So P sub z is equal to 197 newtons. Next, we have to compute the components of Q, or you may write P in vector form. So Qx is 750 cosine of 25, then times negative sine of 25. By the way, Q is directed forward, up, and to the left. So it is only the x component of Q that is negative. So that's why we anticipated it as negative. So this xz component is 750 cosine of 750 sine of 55. It's this angle that is given. So this opposite of 55 degrees is actually equal to this. So 750 sine of 55, then which is equal to this, then we multiply further by sine of 25, and it is negative. So Qx is negative 259.6 newtons. The y component is simply 750 cosine of 55. This adjacent side here of this imaginary right triangle is 750 sine of 55. Cosine of 55. 750 cosine of 55. So Qy is 430.2 newtons. Then the z component, which is positive, is 750 sine 55, which is equal to this. Then this is the component times cosine of 25. 750 sine 55 times cosine of 25. So Qz is 556.8 newtons. So combining the corresponding x components, 165.3 plus negative 259.6, then we'll have Rx equals 165.3 minus 259.6, negative 94.3. Ry is 306.4 plus 430.2. So that would be 736.6. And Rz is equal to uh, 197 plus 556.8, so 753.8. So expressing the resultant in vector form, then we have negative 94.3i plus 736.6j plus 753.8k. So that's the resultant of this first problem. Let's proceed to example 12.2. Let R refer to the resultant of the three forces shown. Given that P1 is 165 newtons, P2 300 newtons, and P3 225 newtons, determine the magnitude of R, the point at which the line of action of R intersects the xy plane. So we use equal ratios here, if you can remember. So Rx as to delta x, R equals Ry as to delta y, equals Rz as to delta z, to solve for those point of coordinates of points of intersection with the xy plane. So given this figure here, so let's define its force into the vector form. So P1 is directed rightward, so it is automatic 165i in vector form newtons. Then P2 is directed backward and rightward. So there are only two components, x and z. X is positive, z is negative. So P sub 2 in vector form is 300 times sine of 25, that's P2x, sine 25i, then negative 400 cosine 20, 300 cosine 25k. So that is P2. So P sub 2 is in vector form 126.8i minus 271.9k, while P3 is backward and upward. So there are two components, y and z. So we describe it as 2 to 5 times sine of 40j, then minus 2 to 5 cosine of 40k. So 2 to 5 sine of 40 degrees j plus negative 2 to 5 cosine of 40 degrees k. So in vector form, P3 is 144.6j minus 172.4k. So combining like terms, combining the i's, the j's, and the k's, that would be the components of R. So R is 291.8 plus 144.6j minus 444.3 Newton. So that's the resultant. So its magnitude is square root of 291.8 square plus 144.6 square plus 444.3 square. So its magnitude is 550.9 newtons. Then for the uh, point of intersection of each line of action with the xy plane, so we expect that the resultant is going in that direction. So it is rightward, upward, and backward. So that should be the case. And we will denote the coordinates as x, y, and 0 because z is 0 on the xy plane. So by similar ratios, so we have 291.8 as to terminal minus initial. So this point, initial point, the intersection of all these forces, lines of action of forces, would be at 0, 0, positive 3. So delta x is x minus 0. So 291.8 as to x minus 0 equals 144.6 as to y minus 0, y minus 0. Then equals negative 443.3 as to 0 minus 3. So negative 444.3 as to 0 minus 3. Solving for x, x is, although this ratio, because this ratio is positive, so it is, so x is 3 times 291.8 divided by 444.3. So x is 1.970, while y is 3 times 144.6 divided by 444.3. So y is 0.9764 meters. So therefore, the point of the intersection of the line of action of R with the xy plane is at 1.97, comma 0.9764, comma 0 close meters. So that would be the answer for this problem. So let's proceed to the third example. Three concurrent forces have magnitudes and directions as follows. P1 75 kilonewtons from 040 meters to 400 meters. P sub 2 120 kilonewtons from 040 to 403 meters. And P3 equals 180 kilonewtons from 040 meters to 203 meters. Determine the resultant force. So let's these three forces are concurrent about the point 040. So let's draw the figure, the plane, the XYZ coordinate axis. So let's locate 040. It's there in the y-axis. Then the first force is from that point to 400, so on the x-axis. So there are only two components, x and y. 0 along with z. For P2, 120 from 040 here to 4x, 0y, then 3. So there. So this is 120 kilonewtons and that point is 403. And finally, P3, 180 kilonewtons from the same point, 040 to 203. So 20, then 3. So it's there, P3. So resolving its force into its components, So 75 times, for the first force, 4i minus 4j. So 4 minus 0 is positive 4, 0 minus 4 is negative 4. That's why. And 0 minus 0 is 0. Divided by square root of 4 square plus 4 square plus 0 square. There's no z. So in vector form, P1 is 53.03i minus 53.0j quantity kilonewtons. P2 in vector form is 120 times the quantity 4 minus 0, so 4i, 0 minus 4, negative 4j, 3 minus 0, 3, positive 3k, divided by square root of 4 square plus 4 square plus 3 square. So in decimal, P2 is 74.76i minus 74.76a plus 6.22k. And finally, P3 is 120, so 2 minus 0, so quantity 2i, 0 minus 4, negative 4j, then 3 minus 0, 3k over 2 square plus 4 square plus 3 square, square root. So P3 in vector form is 66.85i minus 133.7j plus 100.3k. So the resultant can now be computed in vector form, so 53.03, then plus 74.76 plus 66.85i, then negative 53.03 minus 74.96 minus 133.7j, so that would be negative 261.7j. Then for k, we have 0 plus 56.22 plus 100.3, so 156.5 k kilonewtons to four significant figures. So that's the resultant. Okay, let's proceed to example 12.4. So three forces, F1, F2, and F3 act at a point O towards the point A, which is at 2, negative 37 meters, at B, negative 150 meters, and at C, 3, negative 46 meters, respectively. Determine the resultant force knowing that the magnitudes of these forces are F1 420 newtons, F2 380 newtons, and F3 275 newtons. Also compute theta y, the angle that the resultant makes with the local y-axis. So again, we have we have a we have three concurrent forces because the forces act at the origin. So automatic, we describe or transform its force into the vector form. So we'll just put the unit vectors to these corresponding coordinates. So for F1 in vector form, that would be 420 quantity. So distance is 2 square, 2 minus 0 square plus negative 3 minus 0 square plus 7 square. That would be distance 1 square root of 62. Distance 2 is square root of negative 1 square plus 5 square plus 0 minus 0 square. So that would be square root of 26 meters, and distance 3, square root of 3 minus 0 square plus negative 4 minus 0 square plus 6 minus 0 square. So that would be square root of 61 meters. So F1 in vector form is equal to 420, or we compute Rx combined. So 420 x component of distance for force 1 is 2 divided by distance of distance 1 square root of 62. Then for the x component of F2, 380. X component of distance negative 1 divided by distance of 2 square root of 26. Then plus F3, 275 times x component of distance 3 divided by distance 3 square root of 61. So Rx is 137.8 newtons. Ry is equal to 420 times negative 3 over square root of 62 plus 380 times 5 over square root of 26 plus 275 times negative 4 over square root of 61. So Ry is 71.76. So this is another technique of computing the resultant. So we compute the sum of x components of all forces. So this is the other idea. You can also write each force into vector form and do the same thing as what we did in example 12.3. So R sub z is equal to 420 times 7 over square root of 62 plus 380 times 0 over square root of 26 plus 275 times 6 over square root of 61. So that would be 584.6. So in vector form, R is 137.8I plus 71.76J plus 584.6K newtons. That's it. So the magnitude of R is 604.9 newtons, and that is square root of 137.8 square plus 71.76 square plus 584.6 square. Cosine of theta y is Ry, 71.76 over R, 604.9. So theta y is equal to 83.19 degrees. So that's it. Then example 12.5, a pole is subjected to the forces shown and a tension force in the wire of 600 newtons. The uniform pole weighs 500 newtons. Determine the resultant of the forces and indicate where it intersects the flat ground. So here is the solution. That's the figure. So the weight is not yet placed. So this is F1. It is specified in vector form already, newtons. F2, this is downward. So that's negative 300J. F3, that would be the weight of the pole. So since this distance is 4 and the pole is uniform, so this is the center of gravity of the pole, so the weight acts there. And we have negative 500J in vector form, so let's call that F3. Then let's call F4 as the tension in the wire, and that is F4. Then in vector form, its magnitude is 600, so 600 times it is directed forward, down, and to the right. So only the y component is negative. So in vector form, F4 is 600 times 5i minus 4j plus 3k divided by square root of 5 square plus 4 square plus 3 square. The forces, by the way, are concurrent and not coplanar because F2 can be moved along its line of action and it can be transferred at this center of gravity of the pole. So they are concurrent. So F1 is negative 300J. F1 is given negative 120I plus 180J plus 150K newtons. F2 is negative 300J in vector form. It's bold face there. Then F3 is negative 500J, which is the weight of the pole. And F4 is 600 times 5I minus 4J plus 3K over square root of 5 square plus 4 square plus 3 square. And in decimal form and vector form, 424.3I minus 339.4J plus 254.6K. So now that we have written all forces in vector form, then we can compute the resultant. Then it is negative 120 plus 424.3, so 304.3I, 180 minus 300 minus 500 minus 339.4, that's negative 959.4J, and 150 plus 254.6 is 404.6K Newton. So that's the resultant. Then for the coordinates of the point where the line of action of the resultant crosses the ground, the flat ground. So the flat ground is the XZ plane, and we describe the resultant as rightward, downward, and forward. So therefore, we expect positive coordinates for X and Z. So let us say this is the intersection of the resultant with the ground. That point would be at the coordinates of the X, Z, and Y is 0. So delta X is X minus 0. This is at 0. Y is 4 and Z is 0. So 0, 4, 0. So Fx 304.3 as to delta X, which is X minus 0, equals Fy negative 9.4 as to 0 minus 4. So as to 0 minus 4, then equals Fz 404.6 as to Z minus 0. So again, this ratio is positive. So if we solve for X, it's 304.3 times 4 over 959.4. So it is 1.269. Z, on the other hand, is 4 times 404.6 over 959.4, so 1.687. Therefore, the resultant crosses the ground at the point 1.269, 0, 1.687 meters. So that's the answers to 12.9. Let's proceed to the next example. 12.6. Three tensile forces, of which one is shown at the origin. One of the unknown forces has a magnitude of 240 newtons and passes through the point 3, negative 4, 2 units. And the second has a magnitude of 300 newtons to negative 153 units. So determine the resultant. So this is the figure. So we will call this the third force, and each force should be expressed in this time in vector form. So the first force is 240 times quantity 3I minus 4J plus 2K all over square root of 3 square plus 4 square plus 2 square, because the initial point is the origin. So in decimal and vector form, F1 is 133.7I minus 178.3J plus 89.13K. F2 is equal to 300 times the quantity negative I plus 5J plus 3K over square root of 1 square plus 5 square plus 3 square. And in vector and decimal form, to 4 significant figures each. So it is equal uh, to this value here. F3x is, this one is F3x, so it is directed backward, up, and to the right. So it's only the z component that is negative. So to solve for fx, we solve this xz component first, which is 500 cosine 40, then multiply that further by cosine 15 to get the f3x component. f3y is simply this height of this right triangle, so it is 500 sine of 40 f3y. So it is equal to 321.4 newtons, and f3z is 500 cosine 40, which is the xz component. Since it is backward, so we multiply further by negative sine of 15. So 500 cosine 40 times negative sine of 15 degrees. So that's f3z. It is equal to negative 99.40 newtons. So in vector form, f3z would be equal to 370.0 I plus 321.4 J plus 99.14 K newtons. So the resultant can now be computed, and is simply adding the corresponding components. So R is 153.7 minus 50.71, then plus 370 I, then negative 178.3 plus 253.5, then plus 321.4, so 396.6 J, then 89.13 plus 152.1 minus 99.14, so 142.1 K quantity newtons. And lastly, or last example, three forces, of which two are shown, act at a point on a particle as shown. The third missing force of magnitude 20 kilonewtons is directed from the point of application 3 units rightward, 2 units upward, and 4 units forward. Determine the resultant. So let's make this third missing force as F3. So this is the given figure. Let's consider 28 kilonewtons as F1. So F1x is, it is directed backward, rightward, upward, and rightward. So only the z component is negative. So as usual, we first solve for the xz component, then multiply that further by cosine of 20 to get f1x. So f1x is 28 cosine 25 times cosine 20. So f1x is 23.85 kilonewtons. F1y is 28 sine of 25. So it is 11.83 kilonewtons. F1z is negative. So it is 28 cosine 25, then times negative sine 20. That's F1z. So F1z is equal to negative 8.679 kilonewtons. So let's call 36 kilonewton as F2. It is directed forward, up, and to the left. So the x component is negative. So as usual, we first solve for the xz component, which is 36 cosine 50. Then we multiply it by negative sine 30 to get the x component. So F1, by the way, in vector form is 23.85i plus 11.83j minus 8.679k. So F2x is equal to 36 cosine of 50 times negative sine of 30. So F2x is negative 11.57 kilonewtons. F2y is 36 sine of 50, this vertical component. So it is positive 27.8. F2g is 36 cosine 50 times cosine of 30, which is positive. So 20.04 kilonewtons. So in vector form, F2 is negative 11.57i plus 27.58j plus 20.04k kilonewtons. Then F3, which is the missing force in vector form, is 20 quantity 3i plus, because these are all positive, so 3i plus 2j plus 4k divided by square root of 3 square plus 2 square plus 4 square. So in vector and in decimal form, F3 is 11.14I plus 7.428J plus 14.86K kilonewtons. So combining similar components, so the resultant is equal to 23.85 plus negative 11.57 plus 11.14, that's for I, and for J, 11.83 plus 27.58, then plus 7.428, 46.84, then for K, uh, negative 8.679 plus 20.04 plus 14.56, so you get 26.22K kilonewtons. So you notice that it's easy to compute the resultant of non-coplanar concurrent force systems by simply expressing each force into its rectangular components. And if you want to have a review, you refer to the previous slides, previous videos that I have on force resolution. And it's easy to compute the resultant force in vector form. And if it is required to determine the point of intersection of the resultant with some pair of or some plane, intersection with some plane, and you apply the similar ratios in order to locate the point of intersection with that plane. So I hope that you find the solutions easy. You find them easy because it's a matter of resolving each 3D force into their rectangular components and combine the corresponding X, Y, and Z components. So that's it. So thank you by the way for watching, and don't forget to subscribe so that I will be inspired to do more lecture videos. And I hope that these videos that I uh, made will be useful in your studies. Thank you and goodbye.